Can we do the first part of how to find a z-score, the part that we did like before we started using it in SALT?
Before we did it in SALT, okay. So we're looking at how to find z-scores, okay? Now they're different. Well, they all end up being the same formula, but they might look different. So suppose you collected the sample and the mean of that sample was, say, 30. So let's suppose we gave a quiz out of 40 and the average was 30, and that the standard deviation was 10, and that it was a class of 50 students. And if you wanted to get a z-score from this, you need to calculate a guy called the standard error, right? And the formula for getting that, in this question at least, would be S over the square root of n. So you take 10 and you divide it by the square root of 50. And so you end up getting 10 divided by the square root of 50. And that ends up being about 1.414. So the formula now for getting the z-score in this situation would be, and you need to know, or be told at least, that the population mean was 35. So let's say he's given this test to lots and lots of classes over the time, and 35 was the usual. So it's going to be x take away mu over the standard error. So we would do 30 take away 35 over 1.414. And I'm going to do a mistake in the calculations. It's going to be 30 take away 35 divided by 1.414. And so what is wrong? What's wrong in my calculation?
You didn't put the brackets in.
Okay. So 30 take away 35 divided by 1.414. And in this case, the z-score would be negative 3.536 and so on. Now that's one situation where you may get the z-score. Here's a different story. Let's do an IQ story. We know that the mean of IQs is 100, and we know sigma equals 10. This are population parameters. So a population parameter is a number from the entire population, right? So we've done a census and we got it, right? There is no wiggle room, right? And one person takes an IQ test, and they take the IQ test and they get 132. And what you might be asked to do is find the z-score for this one person. Well, in this case, the z-score will be what they got, take away the mean, divided by the standard deviation. Now, do you notice that sigma doesn't have any dividing by n's going on, right? It's just sigma this time. So in that second story, when the data you get is population data and it's a one-person deal, this is your z-score. It's got the number, take away the mean over some kind of standard deviation. In this case, it's 132, take away 100, divided by 10, and this ends up being 3.2. Now, this kind of z-score can also have an extra question added to it. You could get other things with this one as well, but you might get a question like, is a score of 132 in an IQ test considered as an outlier? In other words, if somebody had an IQ score of 132, is that exceptionally big, right? Outliers are bigger than the norm. And there's a very simple test for it. What does a Z score have to be bigger than to be considered an outlier?
3.
It's 3. We haven't done so many, but it also works the other way. If you are less than -3, aren't you also an outlier? It just means you're exceptionally low. You know, like American football players, right? Really low IQs. Now, you can also use Z scores in yet a third way. And that is the Maggie against Brandy. You don't know this, but you two are long lost sisters. And you found out that and you did an IQ test, or no, you did a test and you compared them. And Maggie, you got a score in your test of 73. And in your class, we'll call it you, in your class, the mean was 60. And the standard deviation in your class, I'll call it sigma, was 10. Brandy, you did better. You got 75. And in your class, the mean was 65. And in your class, the standard deviation was 6. And so what we're going to do is we're going to compare both your scores, essentially to see who did better. And who did better means who got the biggest Z score. So we'll try Maggie first. Maggie, do you think you did better? Even although your score was lower, wasn't the average quite low? So you did well in a difficult test. Brandy, do you think you beat her? You got more, but in an easier test. It's hard to tell, isn't it? That's why we have Z scores. So the Z score for Maggie is going to be what she got, take away the mean, divided by standard deviation, right? So it's this version. And she got 73. You took away 60 and you divided it by 10. So she had 1.3. Let's see what Brandy did. Well, she got a Z score. Well, she got 75. Take away 65, divided by 6. And that ends up being 1.33. So the conclusion is, didn't Brandy do just a little bit better than Maggie? Now, if I'd adjusted this number and made the mean bigger or smaller, or I adjusted this number and made the standard deviation bigger or smaller, that would definitely affect this guy. I could tweak it and make this smaller. So she ended up with 1.2. I could do that two ways. I could do it by making the standard deviation a larger number or making the mean, a larger number as well, right? I could tweak it that way. I could, oh, I've got an itchy nose, that means I'm going to get angry. Y'all know that superstition? Itchy nose means you're going to get angry. God, Americans are not superstitious. I have hundreds of superstitions. Do you know what an itchy, this is just to do with scratching, right? Being itchy. Itchy nose means you're going to get angry. What does an itchy ear mean? Someone is talking about you. That's what it means. If you have an itchy left hand, you're going to lose money. So don't go gambling. And if you have an itchy right hand, you're going to win money. You should go gambling. If you have an itchy foot, what does that mean? You're going to go on a journey, right? You're going to travel somewhere. And that is just superstitions based on being itchy. Can you imagine how many different superstitions I've got? None of them at all are based on science, right? And I blame my mother for that, because my mother was really quite superstitious. So go figure. Right, that was a good question. There's lots of other Z scores, situations, but I hope I've covered at least enough to give you a taster of them. What do you want next? Any suggestions?
Matrix of die.
A bit louder, Maggie, sorry.
Can you do one with a die matrix?
One with a die.
Like where you set it up into the grid?
I'm trying to think what that question looks like. Something to do with a dice and building a table? Is it that one? One dice or two dice? Because they take forever if it's two. Two dice, okay, yeah, it's two dice. You wouldn't be expected to create the table, and I'm not going to create it either. I'm just going to give you a taster of what it might look like. So you'd have your first dice, and then you could have your second dice. And part of the table might look something like this, right? Your first dice could be a 1, a 2, a 3, a 4, 5, 6. Second dice could be a 1, a 2, a 3, a 4, 5, 6. And in here would be first dice, second dice. So that's first dice, second dice. Then it would be 2, 1, 2, 2 forever. And going down this way then, and you're looking at 1, 2, 1, 3, and finally 1, 4. Now I want you to imagine that I did the entire table. Otherwise we'd be here for the next 10 minutes while I did it. You can then answer questions involving what happens when you roll two dice. So probabilities are made up of two numbers typically. The top one is the number of ways whatever event A is. So it's meant to say event A here. Can happen. And on the bottom, it's the total. Right. Now, if you roll two dice and you build this entire table, you can actually predict how many answers are going to be. Isn't there 6 rows with 6 columns? So there are going to be 36 ways in which two dice can be rolled. So I know that the answer is going to have a bottom number of 36, typically at least. So suppose I went and said to you, what's the probability that you roll two dice and the total is 5? Then what you need to do is you need to find all the ways in which you could get a total of 5 when you roll two dice. Now, I've not got all of them here, but would you agree those two add up to 5, right? This one here would add up to 5. This one here would be add up to 5. And if I put one right up here, wouldn't that one also be adding up to 5? In fact, isn't there only 4 different ways in which a dice could add up to 5? So the probability that you get a total of 5 is 1/9. Now you can ask lots of different kinds of questions with dice. For instance, I could say to you, what's the probability that I get a pair, right? 2 3s, 2 5s, something like that. The bottom number is 36. How many pairs do you get in a dice? Like a double 1, a double 2, so on. How many of them altogether are there? Double one,
Six.
yeah.
Six.
Double two, 3, 4, 5, 6. So the answer to that would be a 6. You can do a question that is a conditional probability. What's the probability that at least one dice is a 2, given that the total was 5? Now, when you get a conditional probability, you are actually told something has happened. In this case, you've been told that the total was 5. And I've picked that one because I've already got the answer. Do you see? This means that has happened, right? And there are only 4 of those. Do you notice that the bottom number now changes depending on what they've told you? Now, out of only those 4, how many of them have a 2 in them? Well, that one's got at least 1, 2, so does that. So there are 2 of them altogether. And that ends up as a probability of a half. Are we good with that one?
I don't get why. What is the what? Why is there only 4?
If you look at my little pattern up here, these are the only ways you can get a total of 5 when you roll 2 dice. A 1 and a 4, a 2 and a 3, then you get a 3 first and a 2, and then you get a 4 first and a 1. So there are only 4 ways to get a total of 5. So if I tell you, right, given that the total is 5, then the bottom number is those 4 guys, right, those 4 ways. And now I look at only those 4 guys, nobody else. How many of them have a 2 in it? That's what that's essentially saying. And this guy has a 2 in it, and that guy has a 2, and that's where the top number came from. So the bottom number is how many ways could you get a total of 5, and the top is how many of those 5, right, how many of those total of 5, right, there's 4 of them. How many of them have a 2?
At the same time or and
Oh God, it must be my signal today because I'm not really hearing you at all. I'll turn the sound up as high as I can. Try that again for me, please, Cody.
okay, so the probability at least one dice is a 2, and the line is an and or same at the same time.
That is the symbol we use for given. So if I'm picking it up right, the probability that at least one of your dice is a 2, given that the total was 5. Right. So that line is the symbol that we use to replace the word given or given that. Right, let's do another one. What's the probability that you get a total of 7 given one of the dice was a 3? Right, if I tell you one of the dice is 3, because I don't have that big 36 guy in front of me, I wished I knew that question was coming, I might have found one. Let's look at the given piece of information. One of the dice was a 3. So I'm going to write down every dice I can think of where one of them is a 3. So I could get a 1 and a 3, a 2 and a 3. Why am I not doing a 3 of a 3? Why am I not doing a pair of 3s?
One dice is a 3.
Yeah, if I had said at least one of the dice was 3, see the difference a word can make? If I'd said at least, then I would have used it. But since I said one of the dice, so 3 3s isn't going to work. They're going to be a 3 4, a 3 5, and a 3 6. And I have spoilt my thought process. A 1 2, a 1 3, a 2 3, a 4 3, a 5-3, and a 6-3, right? In other words, I'm writing down all the threes being second. And can't you also get it the other way around? I'm trying to be consistent in the way I write them. Would you agree that that's the only ways that you can get a 3? Right, that's every single one. And if I count them up, there's 2, 4, 6, 8, there's 10 of them. So I know that the bottom number is 10. 10, because that's all the ways one of the dice was a 3. Right. Now, the total has to be 7. We only look at these guys and we find the ones that have a total of 7. Would you agree these are the only 2 out of the 10 that have a total that equals 7? So that tells me the top number. And so the probability is 1/5. So conditional probabilities using dice. Okay, let's do a simple one and then we'll leave these guys. What's the probability that you get a total that's even? So there's 36 out there. How would you get, you don't need to tell me the answer, but how would you find all the dice out of the 36 that had an even total?
Half right.
Didn't catch what you said. I heard right, but not the first one.
Half.
Half, so 18 seems reasonable.
Mhm.
I'm not saying it's not, because I don't know yet, but I'll find out. Shouldn't you go to the 36 of them and say, you add up to an even, so I'll put a little asterisk, you add up to an odd, you add up to an even, you add up to an odd, you add up to an even. There's 3 in that row, 3 in that row, 3 in that row, 3 in that row. I'm now convinced you are right. It's going to be half. But if I had the whole grid in front of me, couldn't I just go 1, 2, 3, 4, 5, 6? Just add them up. There's 18. It wouldn't take me that long. And that would be it. Is that the kind of things you were talking about, Margaret?
Yes, thank you.
Right. Don't worry about creating that table. If I ever did that question, you would be given the table so you could just use it in front of you, because it would take you forever in a day to do one.
Okay, so
Mm-hmm.
I mean, it's related to the dice, I guess.
Okay, Tamar, what's the question?
What are all the things that go inside the probability parentheses? Like there's the given, there's at the same time, there's or, and, or if, right?
Oh, yeah. Okay, so we have, I think I got your question. So you might have, what's the probability of A and B? You get probability A or B,
Mhm.
and you get the probability of A given B, right? That's the 3 main keywords that are used in probability: ands, ors, and given. I'm going to use cards this time because they're a little bit easier and we can imagine them. So you might be given a question like, what's the probability that you get a king and a red card? Now, I want you to think of that as basically meaning you get both things happening. So if I was doing that in my head, I would just say red kings. That's how I would interpret it, right? So that and is like both things happening at the same time. So there are 52 cards in a deck, but how many of those are kings in red?
So half again.
Both things at the same time.
Is
That
it
means red
2?
kings. It is, it's 2. Both at the same time.
Oh, kings.
Right? So if you were just saying reds, it'd be half of them, right? If you were saying kings, it would be a lot less. It'd be a 13th, for instance. But there are only 2 red kings, so that ends up being 126. So you think of that as kind of meaning both, right? Both at the same time. That's probably a better phrase, right? Now, if you do an or, It's a little bit different. If I said to you, what's the probability of getting a king or a red? That is a little bit harder to count, because you want to basically add up all the ways in which a king could happen, or, totally unconnected, I guess, all the reds. So this would look like this. The number of kings plus the number of reds. And I wish it was as simple as that, but it's not, because won't you double dip if you do those two numbers? So you have to remember to take away the both. So what do I mean by that? If I look at a normal deck of cards, would you agree that there are 4 kings? Right. A normal deck of cards, there are 26 red, right? 13 red hearts, 13 red diamonds. Now, how many of those 30 cards, right, are double dipped? In other words, how many are red kings?
2 of them.
Yeah, we can use that up here. And so the answer isn't 30 out of 52, it's only 28 out of 52, which you can divide by 7, I believe, and get 4 13ths. No, you can divide them by 7, you can divide them by 4 and get 7 13ths there. That's what I meant to say. So that's a king or a red. Do you see that an and is really both things happening? An or is one and or the other happening, right? Now the third one are called conditional probabilities. So let's see what that would look like. What's the probability that you get a king given that it was a red card? So you know that it's a red card. The given changes the bottom number typically. So in a normal deck of cards, if I tell you it's a red card, right, I'm looking at it and say, hey, I'll give you a clue, it's red. Doesn't that make it 26 on the bottom? And now you have to remember that you're only talking about red cards when you go here. Now, normally when I say, what about a king? Wouldn't you say 4? Because there's 4 kings. But now I'm telling you it's red. How many of those are kings?
2.
2. And so 1/13. Do you see how the same pieces of information interact in different ways? And you get different answers to probabilities that use them. Okay. If I told you that the probability of getting A given B was the same number as the probability of A, you can make a conclusion. And the choices are A and B are independent, or A and B are dependent. And I like the word dependent instead of the word not independent, but that's me, right? Because sometimes they call it not independent. If the probability of A given B is the same number as just calculating the probability of A, which of these two is the conclusion that you will make?
Say that again.
If the probability of A given B is the same number as the probability of A, then A and B are independent or dependent. Which is it?
Independent.
Correct. And if this guy is not equal to that, the answer will be dependent. This is a test for independence, right? You find this probability and you find that one. If it's the same number, independent. If the two things are different numbers, they are dependent.
How do we figure that out?
Oh, you calculate them. So suppose I went and said to you, what's the probability that you get a red card given that it was, say, a king, right? Let's just say that. Right, I know that there are 4 kings in a deck. Right? How many of them are red?
26?
How many are red
Two.
from the kings? There's only 2 of them.
Two.
And so that's a half. Now, what's the probability then of just picking a red card? Well, that's a half, isn't it? Oops. Now, do you see that these are the same? Think of that as my A and that is my B. Isn't the probability of A given B, which is a half, the same thing as the probability of A, which is a half? So that means red cards and picking kings are independent events. In other words, if you got a red card, it does not have any effect on the chances that it's a king, right? It's just as likely to be a king, you know, whether it's red or not. And the vice, you know, the opposite is going to be true. Okay, we seem to be spending a lot of time on probability today, but that's fine. Whatever is useful, I'm cool with that. What's the next fella? What's the next topic?
Can I ask a specific question?
Sure.
Test 6, question 7.
Okay, hold on a minute. I'll go hunting for it. Test 6,
Mhm.
question 7.
Yes.
So we back in the day. Past assignments. Feels like forever, doesn't it?
Yeah, it does.
Sometimes.
Like we've
Okay,
known each other our whole lives.
I wouldn't quite take it that far, but I get the gist of what you're saying. I'm still trying to find it because, oh, come on, behave yourself. I'm hitting the wrong button each time and I keep repeating the same mistake. So past, I was trying to reschedule it, which was not what I need to do to find it. There we go. And I'll view it. Right, so this is test 6. Oh, God, I'm getting tired. I just found test 6 on 142. Let's find it on 146. There we go. That's better. Okay, where are you? Test 6, test 4, test 6. Okay, what question number was it now?
It was question 7, part A. I just needed it explained to me because
Sure.
I see the answer and it's not clicking.
Okay. I'm looking at the answer myself and I'm trying to think why that is what they said it is. Oh, now I know. Okay, you have in question 7, probability distribution. And it looks something like this: 0, 1, 2, 3, and finally 4. And it's got, you know, the probability here and the guy called X. And probabilities that we have are 0.1, 0.03, actually that's 0.1, 0.05, 0.39, and finally 0.52. And they ask you for a really interesting, but not a typical question. And they ask you for the median number, the median value of X. So I'm going to start with 0 and go 1, 2, 3, and 4. And think of this as like a number line where you line people up from the smallest to the biggest, right? Now, if it was just 0, 1, 2, 3, 4, wouldn't the middle number be 2, right? And that would be the case if every single one of these was the same probability. But this has very weak probabilities at the beginning and a really strong one at the end. So what you're really going to be looking for here is where would the probability be 0.5, right? So which one of these numbers would you eventually get a probability of 0.5? And if you started with this first one, and this is the long way of doing it, that guy is 0.01. By the time you got to that, you're now up to 0.04 because you add those two together. You go to here and you're at 0.09, and you go to here and you're 0.48. All I'm doing is adding. And then if I go to here and add that guy, I get 1.00. So when you're looking at this, where is 0.5 going to be? And 0.5 very roughly is about here. And that's one of these fours, because the fours, after a 3, everybody's a 4, right? After a 2, everybody, right? And everybody, and so on. So we are looking at essentially 4, and that was the answer. Not a very nice question, and no, I won't do that in the test. But that's the answer. It would be a 4.
Thank you. I didn't understand that one.
Yeah, let me do another version because I'm not convinced I gave a very good explanation either. So let's have 1, 2, 3. Oh, I guess we're having 4 again. And let's change the probabilities now. 0.2, 0.2, 0.2, and 0.4. Right, let's do that one. So I'm going to start at 1. And 0.2, up to 0.4, up to 0.6, and finally finishing at 1.0. Would you agree that 0.5 would be between the 2 and the 3? And once you leave the 2s, everybody's a 3. So the answer to that one would be 3. So the median of this data would be 3. Are we cool with that? Well, I've covered it, and I'm not going to give you a test.
I did.
question.
Sorry, I was muted. I got it. Thank
No,
you.
that's okay. I don't like this question. I hope there are not too many like that. Sometimes the odd weird one sneaks in with WebAssign. You know, I didn't even realize I put that question there. Okay, what's next?
I have one quick one from the midterm. It's question 8.
Okay, hold that thought. I'll have to go to a different place for that. And where in the heck did I put the midterms? Ah, where did I put the midterm? I'm still looking for it. Have you got the question? Oh, I think I found it. Okay, I found it. Okay, and it was question 8, you said? Was that from the ones that we wrote the answer, or was that from the WebAssign? I should have asked that first.
The WebAssign one.
And in which case I didn't need to do any of what I just did there, because I should be able to just go to the WebAssign. And now I have to find it. There we go. And do a view. And what question was it?
8.
Okay, midterm question number 8. That's towards the end. So you are told in question at least in the one I've got, that the mean was 72 and that the standard deviation was 9. And you're being asked to find the pulse rate that would be the 10th percentile. So give me a little visual. Can you imagine right in the middle is 72? A 10th percentile would be a guy over here, such that in there was only 10% of the people, right? 0.1. Now there's a salt button that you need to do that question. So let me show you how you would do it. So we're going to hit salt. And well, it's nice, but if it hadn't done it, you would make sure that you were in the normal distribution for this question. Now the mean in this case was 72. The standard deviation in this case, my case at least, was 9. Now this one is set up exactly the way I wanted it. See how it's shaded to the left? But I want this number here to be 10%. And so the answer is that guy. So you would need to get a pulse rate, say to 1 decimal place, of 60.5 to be in the 10th percentile. So let me return back to the white screen. That number there would be 60.5. And that might mean, if it was a doctor that was interested in this, that if you are in the 10th percentile, your heart is beating really slowly, right? Now that might be some concern to them, right? It's actually strange. It depends on the person whether that's a bad idea. Do you know, if you're a really, really fit athlete, your resting pulse rate can be really slow because you've got a really strong heart and its pulses is beating a lot of blood, and you've got a lot of room for maneuver, so that when you run the 100 meters, you know, it can go over here, but it's not that bad, right? If you started off here and you tried to run 100 meters, do you see you could have big problems, heart attack material. So, but if you're a sedentary person and you're overweight and all sorts of other things, couldn't that be a really bad sign that your heart ain't working well? Right. So a doctor would like to know things like, what is a really low pulse rate, right? And what is a really high pulse rate? What is a really low blood pressure? What is a really high blood pressure? And so they make those little intervals if you ever get your blood tested, where they say you're in the normal range, you're in the high range, you're in danger zone range, or low range, really low range on the other side. And they get them using these percentiles. So somebody who was doing the SAT and was the 99th percentile, wouldn't you be going, whoa, that guy, right? Guy means boy or girl. That guy is really up there, isn't he? He's got great, great SAT.